My name is Ben Simpson, and today I'm going to be doing a presentation on bioconcrete. So first off, there is a major problem with traditional concrete because it is prone to crack formation and propagation. So it means that cracks can easily form in concrete since it's technically a ceramic, and that means that there are only ionic bonds holding together the layers, which means that it's very easy to separate with water or earthquakes or shaking or any of the like, or just wearing over time with degradation. And then once those cracks are formed, then they're allowed to propagate pretty easily through the concrete, which means that the cracks become bigger and bigger and bigger over time, causing them to weaken the entire structure of the concrete, because the end of a crack acts as a stress concentrator. So if you're pushing down on it, a lot of that stress is going to the end of the crack, which is causing extremely tough stress to be applied to that location on the crack. So critical concrete infrastructure often requires routine expensive maintenance because of this cracking. And as you can see in the chart on the bottom left, both contractors and design team members say that cracking is the leading cause of concrete design damage. So it's really a huge problem with concrete, is that these cracks are able to form and then they're able to propagate through the concrete. Really, it's over a $2 billion industry. Concrete repair, production and distribution of the solutions for concrete repair is an over $2 billion industry, because this is such a large problem on a global scale with large infrastructure projects and local projects, and pretty much every project involving concrete is this crack formation and propagation, which over time weakens and crumbles really the concrete. And over time, as our infrastructure continues to slowly crumble because of these cracks, that will cause the only more demand for concrete repair. So let's look at biology for a solution to this crack problem. So certain kinds of bacteria, including Bacillus sphaericus, can produce limestone, which is a very hard material. I'm sure you're familiar with it. A very common material from a special calcium lactate compound. And this bacteria can lay dormant for around 200 years, which is well after we're all going to be dead and the concrete will have served its purpose. So if this dormant bacteria is exposed to the calcium lactate, it's able to convert this soluble calcium lactate into insoluble limestone, which produces it as a solid out of the reaction. So we're able to take advantage of the fact that this reaction produces solid limestone from bacteria by forming little bubbles of calcium lactate inside of concrete that are surrounded with biodegradable plastic shells. So if you can see in the concrete on the bottom left, there's little black dark bubbles speckled throughout. Those are bubbles of this calcium lactate solution, which is able to be processed by that bacteria into limestone. So the dormant bacteria is placed throughout the rest of the concrete. Just the normal concrete, gray grit concrete, has a bit of bacteria in it. And when a crack makes its way through the surface of the concrete and into one of those dark bubbles, then it's able to expose the plastic shell that's biodegradable to the elements. And then it's able to degrade down that plastic shell and expose the calcium lactate. So when that calcium lactate is exposed by the removal of that plastic shell, the bacteria is basically able to get to work and convert that calcium lactate into limestone. So as this reaction occurs, turning calcium lactate into limestone, limestone is formed as a solid inside of the crack, going from the inside where it reaches that dark bubble to the outside. And over time, the solid limestone accumulates and fills the crack, which allows both the prevention of further crack propagation and allows the concrete to regain the vast majority of its structural integrity, because now it's a solid. There's no crack, there's no stress concentration, there's no gap in the concrete. So some societal implications for this is that basically this bioconcrete is self-maintaining. That whole $2 billion concrete repair industry will be dramatically decreased, because with bioconcrete, there's no need for maintenance because it's self-maintaining. So this cost overall, just the cost of having concrete infrastructure will go down a significant amount as this bioconcrete is able to make its way through society and regulations and all that. Then there are even some really beneficial ecological impacts to using bioconcrete, because it is able to increase the lifespan of the concrete. Because these cracks are not allowed to deteriorate, the concrete will last longer because it won't be crumbled slowly by these cracks forming and propagating. So overall, our concrete production can be reduced, because if our concrete structures last more time, then we don't need to produce as many concrete structures and we don't need as much concrete. And concrete production is a leading cause of carbon dioxide emissions. It puts out huge amounts of carbon dioxide in the production. And by using this bioconcrete and increasing the lifespan of our infrastructure, we'll be able to drastically reduce our carbon dioxide emissions, which will benefit greatly our fight against global warming. Thank you.